A function is a relation where every domain value goes to only one range value. So here we have a function labeled in these balloons. Think of this like a light switch on a wall going to a ceiling fan that's got its light turned on. Then the on switch goes to both the light and the fan, and the off switch goes to both the light and the fan. Because the on goes to two things, and also because the off goes to two things, this makes this not a function. You only have to have one domain value going to two things for it to be not a function. Here we have two, but that doesn't matter. For this next one, we have two relations that are graphed with the points, and so we're looking at, do every domain value go to only one range value? Well, the domain values, remember, are the x-axes. So this is the domain value here for these 2 points. This one, the domain value is right here on the origin. This one's right here, 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 and here. And so all of these coordinates, all the x coordinates are the domain value for these points in this relation. And of course, these 2 points have the same domain value. If this was actually labeled as like, for instance, 1, 2, 3, down here, this was -1, -2, and so on, then both of these points, it looks like this one is at the x value is -1, y value is 0. This one here is at x value of -1, y value of 1. And you can see we have two domain values that are the same. The x values are the same. If you were to draw this in a balloon, right, we would have -1 and then 1 and 0. -1 goes to 1 and -1 also goes to 0. So that's the same issue with this one. We have one domain value going to two range values. In this next one, you can see, well, we have a domain value here, 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 and here. These are all the half coordinates. So we have 0, 0.5, 1, 1.5, and 2. And all of these are different. So yes, this is a function. Whereas this one here was not a function. So that's all you're trying to do. You're just trying to see if every domain value goes to one and only one range value. Give it a try in 1 and 2. Now, I was showing you how to look at the domain values going to range values for each individual thing. But for continuous relations, there's actually a better test. We can use the vertical line test. If the relation passes the vertical line test, then every domain value goes to only one range value, and that means it's a function. The vertical line test is quite simple. Just look at these 4 graphs. For this relation, right, if I can take any vertical line, and if I can only find vertical lines that pass it across, that intersect with the relation once, then it is a function. In this first one, I can take any of the vertical lines on this whole thing, and you can see that this does pass. So this is a function. Now this one, I can create a vertical line right here, and you can see it intersects it twice. So that means that this is not a function. Of course, on this one, I can create many vertical lines that cross twice. I can even create a vertical line that only crosses it once, right here on the very edge. This only hits it once, right there. But that doesn't matter. You have to have one, and only one vertical line needs to cross twice, and then it's not a function. You can have infinitely many vertical lines that don't, but if one does, then it's not a function. This one, of course, has many vertical lines, so this is not a function. This one here, very similar. We can create vertical lines all the way up this thing and all the way at the end there. This is a function. And finally, for this last one, again, I can create vertical lines all the way along it. You know, it only ever crosses it once, so this is also a function. And it's important to note the vertical line test is exactly what I was doing up here. Right, for this spot right here, I can create a vertical line right on this one. And you can see it crosses it twice. So that one didn't pass the vertical line test. Of course, this one's a little bit weirder to think of as a graph. That's where these balloons really help to see if it's a function or not. And this one does pass the vertical line test, right? You can take a vertical line across the 5 points, and they only ever cross once. Okay, now, if you have a function that's listed as an equation, you can always just graph it and look. So this one is 3x minus 5xy plus 2y squared equals x. We get this function here, or this relation, I should say, here, and we're going to ask, is this a function? And all we have to do is create a vertical line and see if it crosses it twice. Can you find one that crosses it twice? Of course, this one has many vertical lines that cross twice. Right here on x equal to 1, that crosses it twice. Of course, you can move pretty much anywhere on this direction. It'll always cross twice there. And anywhere on this direction will also always cross twice. So there are many vertical lines that cross twice. So therefore, this is not a function. Give it a try in number 3. So functions are special relations. We like functions because they give us one output for any one input that you have. And that makes a function kind of a machine. Really, we have some kind of behavior, whatever the function does to your input. It's like, think about like a black box where there's, something goes into it. This is our input, and something comes out of it as our output. Of course, our inputs are always going to be the x variables, and the outputs are going to be the y variables. And so the function, the actual machine of the function is the equation. That's what we're typically going to be looking at. But sometimes you're given just a graph and you're not told how the function works. You're just given what it looks like. But it's just a machine where you plug something in, you get one and only one thing out. That's the reason why we write it in this form, y equals f of x. This is our input. The function is the name, f, which is of course the first letter of function, f for function, and then our output is right here. That's the notation for it. You really don't use y at all. You always use f of x. So you probably see something like this: f of x equals x squared plus 2. This is what a function normally looks like. It's a formula where your input is going to get plugged into here. Then your input gets squared and added onto 2, and that is how you get your output. Now, it's important to note that this notation here, f of x, that's how you read it, f of x. F of x or g of y or any name thing with its input, this is not multiplying. It's not f times x. No. This is the notation, f of x. And whenever you see this notation, you can know this is a function that we're working with. Of course, you can have many different names for functions, capital Q, L, M. There's many things. We tend to use F, G, and H because F stands for function. The next letter down is G. The next one after that is H. Also capital letters, capital F, capital G, capital H. I will tend to use subscripts as well. I think subscripts work pretty well. So F1 is different than F2. GI, the I is the index variable. You might see some things like that. Q4. You could also see, for instance, I could say something like H of 3.6. Normally you name something like this because it directly relates to the function, like 3.6 is somehow used in the function. For instance, I could say 3.6x, sorry, 3.6x, where this is the function. You know, it has some meaning to the actual function, but you can name it lots of different ways. Okay, now we can rewrite a normal equation. As long as it has two variables, you can rewrite it into a function. And all you have to do is solve for one of the variables. And what we're going to be doing here is we're always going to be replacing the y variable with our function notation. It's always y because x is always our independent variable. So I'm going to take this equation here, and I'm going to solve for y. So we have 5x equals 3 minus 3y, and you get y by itself. So I'm going to subtract 3. That's going to give me 5x minus 3 equals negative 3y. And now to get y by itself, all I have to do is divide by negative 3. And that's going to give me 5x minus 3 over negative 3 equals y. At this point, all I need to do is replace the y with f of x. So I'm going to do that by flipping it around. F of x equals 5x minus 3 over negative 3. And there is our function notation. So y is not a part of this function anymore. Y is the same thing as f of x. It's also the same thing as our output. So we're going to plug whatever x is into there and solve. And so that's what we do when we actually do plug things in. We're going to plug them in using our inputs. So this is saying, what is f when you plug negative 3 in? What do you get for an output when you plug in 3/5? What is our output when you plug in x plus 7? Here we have an expression being plugged in, not a number. That typically means that we're going to get an expression out of it, not a number as an output. And the same thing is true here. What is the output when we plug in negative x? So let's go ahead and try this out. F of negative 3 equals, we're going to take the exact same expression here, 5x minus 3 over negative 3, except now we're going to change every occurrence of x. Here there's only one occurrence, but you could have multiple ones for different functions. So this x now becomes our input. Our input is negative 3, so we get 5 times negative 3 minus 3 over negative 3. Okay, 5 times our input, negative 3, is going to be negative 15. Negative 15 minus 3 is negative 18. And of course, this simplifies down to 6. So for an input of negative 3, we get an output of 6. All right, for the next one, we have f of 3/5. Okay, our input now becomes 3/5. Five times our input, well, those cancel, and we get just 3. 3 minus 3 is 0. And 0 divided by anything is just 0. So when we input 3/5, we get 0 as an output. Okay, now let's plug in the expression x plus 7. So now, our input is x plus 7 now, instead of 3/5 here. This was our input here. This was our input here. Now our input is x plus 7. So just because we're plugging in another expression with x in it, that means this x changes to x plus 7. That's an important thing to always keep in mind. And whenever you plug in something into a function, it's always a good idea to plug it in with parentheses, because that will clarify. Especially here, you can see we actually need to distribute 5. If you didn't plug it in parentheses, you might miss that, but it's 5 times the input, whatever the input is. And here our input is x plus 7, so 5 times our input, we have to distribute it. 5x plus 35 minus 3 over negative 3. Combining like terms on top. And that is, you could probably do a little bit more with this, but there's not really any need to. This is our output. Not a number, of course, because we plugged in an expression and we get out an expression. So that's kind of what you should expect. It doesn't always happen. Sometimes you do get a number. Everything cancels nicely, but in this case it didn't. Okay, now if we plug in negative x, 5 times negative x minus 3. 5 times negative x is negative 5x. And here everything is negative. And so I can actually move this negative to the numerator because you can move things around as long as it's a multiple. And then distribute it into here. And that's going to give us 5x plus 3 over 3. And I think that's a little bit simpler of an expression. But once again, we plugged in an expression negative x. We got out an expression 5x plus 3 over 3. Okay, let's graph this thing and see how it goes. The nice thing about Desmos is that we can actually type in a function. Double check what that was. 5x minus 3 over negative 3. And it will actually recognize the function input. So if we plug in, you can see that this function is just a line. The line looks like this. If we plug in f of, the first one we plugged in was negative 3, you can see we get out 6. So if you plug in f of negative 3 is right here. If we go up to the function, you can see we get, so we can get it on there, negative 3, 6 is on that function. Okay, if you plug in f of, the next one was 3/5, I believe. Yep. 3/5. You can see we get out 0. F of 3/5 going to 0. That just so happens to be our x-intercept. 0.6 is the same thing as 3/5. So of course we got 0 as a y value, and x-intercepts always have 0 as a y value, so that makes it an x-intercept. Now, when we plug in a different expression, so for instance, f of x plus 3, I believe it was, x plus 7, you can see we actually get a different function. The same thing happens when we plug in negative x. You can see here we actually get a function that goes the other way. And actually, if I remove this purple one, it's actually a reflected function across the y-axis. It's just reflected across there. Okay, give it a try in number 4. Lastly, we have the idea that if the graph is simple enough, like this one is, it's just a nice straight line, and the points are kind of on these grid lines, we can use the graph to evaluate rather than having to plug in to the equation or the function that we have. In this case, we don't know how h of x is, changing the variables. H of x is just given to us as a graph. We can still use the graph to evaluate a function. So here we have h of 3. H of 3 says we're inputting 3. If we input 3, that means that we're taking an x value of 3. X value of 3 is right here. And we're asking, what's the output? And the way we do this is we go either from the input variable, we go either up or down to the function. In this case, we're going to go up to the function. And then we go over and find the y value for this point. The y value for this point is 4. So this point on the function is 3, 4, which means if we input 3, we output 4. For the next one, we have an input of 0, right? This would be the same thing as y equals h of 0. h of 0, once again, our input is 0, so it's going to be right here on the origin. In this case, we do not go up to the function. There's nothing up here. We're going to go down to the function. And we don't go left or right because that's right on the y-axis. This is -2. So this point here is 0, -2. That, of course, is the y-intercept. When x is 0, you have a y-intercept. So this is -2. Okay, the next one says 6 equals h of x. Now, h of x equals the y variable. That means that's the output. We don't know what the input is, right? It's saying x equals what? We were trying to figure out what does x equal. So instead of looking at an input variable to start, like I have been doing here, right? I started at 0, or I did 3 first, and then I started at 0, and then I went down to the function or up to the function. Now we're going to start in the, or with the output variable. The output's always the y, and here we have an output of 6. So we're going to look at 6 on the y-axis. And instead of going up or down to the function, right, we don't go back to -2, right? H of 0 is -2. H of 6 is not -2. Here, we're going to go right, left, or right to the function. In this case, we're going to go right. And this value came from, if we go all the way down, it came from the x value 4. So that means that x equals 4. And just to clarify, what I'm doing here is I'm saying h of 4 equals 6. If you plug 4 in, you get 6 out. That's what we were asking. What do we have to plug in to get an output of 6? Make sure you understand how to read the notation. X is always the thing on the inside. If you know what x equals, or if you know the thing on the inside of the function, in this case we knew what 3 was, then that's our input variable. If you don't know that, but you know the other value, that means it's your output variable you're looking at. So like you have here, we know our output variable, 0. We do not know what our input variable is. So we're trying to find that. So we're going to look at 0 on the y-axis. It's right here at the origin. Go left or right. In this case, we're going to go right to this point here. And that occurs at the input of 1. So x equals 1. In other words, h of 1 equals 0. You always must be able to satisfy this form like I have here. This says h of 3 equals 4. Here I have h of 0 equals -2, h of 4 equals 6, h of 1 equals 0. If you cannot write it in this form, then you've probably done something wrong, or understanding how it works. You've probably done something wrong here. But the big idea is understanding, are you looking at an input variable or an output variable? Here, what are the intercepts of h? Well, we don't actually need to look at the graph because we already found them. These are the intercepts, right? The y-intercept is when x equals 0. Well, that happened right here. X equals 0, that means the y-intercept is -2. The x-intercept is when y equals 0. Y equals 0 is right here, right? You can think of h of x being the same thing as y. That means that the x-intercept is 1. Of course, that's true right here. This is the x-intercept, and this is the y-intercept. Okay, give it a try in number 5.